Almost live from National Semiconductor, the analog IC design and manufacturing capital of the world, it's the Bob Pease Show. Here's your host, Bob Pease.
Good afternoon, good morning, whatever it is, we're here. We hope you're here also. And this is Bob Pease at the National Semiconductor explanation of how things really are. And here's Paul Grohe.
Hi.
And Paul Rako.
Hi, how you doing, Bob?
And you explain what's happening next. I have no idea what's happening next.
You've been on the road doing 30 seminar cities in 30 days, and we're sending you to Europe tomorrow, so good luck. My name is Paul Rako. I'm going to help Bob here. Our show today is ohms, milliohms, micro-ohms, and we're even going to get down to nano-ohms because we've got our staff scientists.
We haven't even discovered pico-ohms, but we're working.
We'll be there next.
It's down there next.
Now, this show is sponsored by LaCroix Corporation. LaCroix develops, manufactures, and markets electronic signal acquisition and analysis products and services. Today, LaCroix's primary products are high-performance digital oscilloscopes, which are used by engineers and researchers to design new and improve existing products in a broad range of industries, including electronics, computers, and communication. I've got my Wave Pro, and I love the thing.
I believe it's good. I've seen you get good data on it.
Oh, it's beautiful. So what are we going to talk about? You got some slides for us here, Bob?
Oh, man, we're going to talk about measuring things.
Cool.
I really like to measure things, such as resistors. Why do I like to measure resistors? They tell us a lot of good, important things. You do have an 80 ampere current times a milliohm. That would be 80 millivolts. That would be 100 dozen milliwatts. That's a lot. You don't want to use a 1 milli. You might want to use a 0.1 milliwatt, a 0.1 milliohm resistor. How do you do that? By using a very low value resistor. How do you evaluate a 0.1 milliohm resistor? You don't just use 1 milliohm and 1 milliohm. You need even lower than 1 milliohm and 1 milliohm. So, to measure this stuff, we could say, we could put in an ampere. We'd have 1 ampere, 200 ohms, 200 ohms. We can twist these resistors back and forth to get low readings.
That nulls out the difference
a perfect
between the two?
null, because the amplifier would say no difference, no difference, no difference, no difference. But now,
like a chopper amp works.
Yeah,
Similar
but
concept.
if we just connected the other side of the amplifier to here, it could cause an error. How could this cause it? Because you might have 1 milliohm, 1 millivolt here, 2 millivolts here in the sense and connection to the resistor. The higher drop in the connection to this could cause terrible error. So you can't just run this directly. You can't just look at this point. You have to look at the balance point on the sense. This helps you cut down the error considerably to bring that to the error amplifier. But still, that is not perfect. Even when the 200 ohm resistors are perfect, 200, perfect, it's not a perfect bridge because when you think about it, 1 inch of 20 gauge wire is a milliohm. 1 milli-inch is a micro-ohm. 1 micro-inch is a nano-ohm.
And that's where we're going to be today,
That's
right?
where we're going to be today. 10 nano-ohms. We have to bridge down to that low level. Now, let's say we have, you can pick that up later, no problem. We have an ampere flowing DC or AC through these resistor bridges. A milliohm here, a millivolt here. But this could be 15 microamperes times 3 nano-ohms is 45 nanovolts.
Not a big signal at all.
Well, 45 nanovolts is 45 part per million of the 1 millivolt signal, which means, if we can't avoid this 45 nanovolt signal, we're in trouble. We're going to lose all our accuracy. So I have a scheme to provide less than 45 nanovolts here, and here, and here, and here, and here, and that is to provide a current Yeah, thank you.
All right.
To provide a current here, such as 8 k-ohms here and 6 k-ohms here, to provide the current. So this IR drop, which could ordinarily be disastrous, could be negligible because there's no current.
So you bleed a little current.
We provide
from
the current
here.
that's well known into this point, so the IR drop is nothing because we don't know or care what this IR drop is, but we don't care because the current is coming past this point in a well-balanced way.
That's fairly big resistor, K, 5K?
A 6K, 8K, yeah.
Just a few microamps coming down there.
And likewise down here, so these currents are all balanced out, and the bridge is substantially perfect. Now, we usually say, what questions do you have? The question is we have now, what is the best way to make a low error amplifier? Well, we take the LM394, which has low noise, very low voltage and current errors. What's the voltage noise? Small. What's the current noise? Small. How do we compare the voltage and the current noise times the RS? How do we do that? We choose this 1/2 milliampere of emitter current for both pairs to provide low noise. So the noise is negligible. Then we take a gain of 10,000 in 2 stages, another gain of 100 in 2 more stages, and another gain of 10 to get the noise down, and the amplifier gain up to get a gain of 10 million of gain. The CMRR is a mere lousy 30 million, but that's not good enough.
That's pretty good.
No, that's not good enough.
Not good enough.
We need a bootstrap. We're going to bootstrap this ground, and the ground for the 12 volts. And
to take the common mode errors.
Bring the common mode up and down so that it works and cancels out all the common mode rejection ratio.
So that's not a fact. So you're running enough current through here to get the voltage noise down, but not too much current because then your current noise
exactly.
goes
If we
up.
ran too much current, that would be excessive, it would be a disaster.
Isn't analog beautiful?
Analog is very,
Had to pick
it's
that
hard
half a
work.
milliamp wasn't an arbitrary
this
thing, folks.
Could be 0.6, could be 0.7, could be 0.4, but we're in the right ballpark to have low noise. Now, at this point, we also say, got any questions, guys? So before we ask any questions, we'll say, do I put in sine waves?
This is how you excite the bridge.
How do I run the bridge? Triangle waves? No. Square waves? No. DC? Well, we can also run DC because we can pull this to the plus rail and we have DC running. And this will be at minus 2 volts with 2 ohms and a current that runs current through here. And all this stuff is running at a well-balanced circuit.
So you're using an audio amplifier
Oh, absolutely.
as a DC power amp.
Yeah, I'm using the LM3876 to provide perfect or excellent DC current gain to provide this -1 ampere until the whole thing runs very stably.
But you're not, I know from advance, you're not going to run it on DC. Now, why?
Well, I'm going to run it at 3 hertz because I've found best low signal to noise at 3 hertz. If I run this at 300 if I run this at 300 hertz, it'd be lousy because I run into the inductance.
All the stray inductance is
But at 3 hertz, I can still see the inductance of this, but it's not excessive, and I get good signal noise from running this at 3 hertz. That's why I picked that frequency.
And then you can cross-plot it on a scope.
Yeah, and I cross-plot this in the scope. The scope gives a cross and up and cross and down and cross and up and cross and down. This is a trapezoidal waveform, and a trapezoidal waveform gives best results.
And that's not a trapezoid because of slew rate limit on this amp. That's
no.
because of this.
We put the triangle wave in here with the trapezoidal result to get out the output with the trapezoid, which is a up and down, up and down. We don't want to hurry things. If you hurry too fast, if I put a square wave in here, it'd be really grouchy.
And then you get the inductance, you get all the headaches from before. Okay. And you get a nice XY scope plot.
Yeah. We avoid putting even the output scope amplifier off scale. This is well behaved and linear. Now, as I say for 1,000 places, we really know how to help you with your analog problems. Does anybody have any questions? I'd be happy to answer questions, but right now I just want to say my favorite programming language is solder.
You don't trust Spice, huh?
No.
He always lies. We found that out.
Well, usually lies.
Usually lies. So
Okay.
we have a guest segment now with Dr. Michael Lauterbach. He's from LaCroix Corporation. He's bringing over a Wave Runner. I wanted to bring my Wave Pro today, but Peggy Alavi's using it to take some fast, high-speed measurements on a comparator that we're going to release. And
Never get it back.
yeah, I'll never get it back. Once they get it off your bench, you never get it back. So let's go look at this, and we'll see what LaCroix has to show us in their new products. Dr. Lauterbach, thank you so much for joining us today.
Pleasure to be here.
Tell us about LaCroix. Where did LaCroix come from? What's the history?
So Walter LaCroix started LaCroix Corporation in his garage in 1964, making equipment for high-energy physicists. You know, the kinds of people who go to accelerators and smash elementary particles against each other and try to make more or different ones.
Is that what your doctorate is in?
It is. That's
You're a particle physicist.
I am. I'm a particle physicist.
Oh, this is great.
So, so what really makes me exciting is when I can measure the track of a single electronic charge more precisely than anyone ever measured it before.
And LaCroix can do those kind of things.
We can do those kinds of things. In fact, that's how the company started. Its first 15, 20 years. That's what we did. More lately, we've become famous for our oscilloscopes. So we've got a couple of them here today. I know this one is your personal scope.
Yeah, boy,
it's from your own bench.
My cold dead hands, will somebody take this from me? I have all my coworkers trying to borrow it because it'll record. You can plug it into the internet and send the data to our data sheet people to incorporate in the data sheets. I'm never giving that thing up. It is the greatest.
Well, that's a Wave Pro scope, and in fact, this scope is the most advanced 3 gigahertz scope in the world. It's the only one that can sample at 20 gigasamples per second, and it also has the longest memory. So you've got the El Primo scope at 3 gigahertz in the world. Today I brought one of the Wave Runner scopes.
Yeah, I noticed a lot of similarities.
There are a lot of similarities. This one has the same core software and mostly the same user interface. So if you know how to run this one, in fact, I would claim actually if you know how to run any digital oscilloscope, you could walk right up to this one and use it.
Yeah,
but if you've already used this one, this one's really simple.
Right. I'm an old analog twiddle the knobs guys, and I got this and no training, no anything, and I was up on it in an hour or two, giving good
So if
news.
you look at this, you can see there's one voltage knob per channel, there's an offset knob per channel. Here's your time base, your horizontal knob. Here's your trigger level, nice knob.
No menus to get to those things.
No menus to get to those things. You just turn them and they're there.
That's wonderful.
So, so in fact, if you change the offset here, you can move it up and down. What we've got here is a signal from a laser driver. Actually, it's a nice National Instruments,
National
Semiconductor part. And it's making a string of pulses, and we've zoomed in on the bottom on a particular pulse that we're interested in. In fact, we captured this in a single shot.
Yeah, all this
we've
data,
got the data captured
we're just
right
looking
here.
at this one little tiny thin pulse out of all that data.
And there's some offset on this signal. So I could move it around and get it to different positions on the screen. But if I ever want to check where ground is, I can just click the offset knob.
So you pushed in.
Exactly. I pushed in, and it's showing me, in fact, that ground is here, and my signal is up here above ground by a certain amount. And then if I click it again, it brings the offset back to where I had it set.
Oh, that's great.
So it's nice. So you can set up your signal where you want it, but then anytime you want to check your ground reference, it's very easy to just toggle back and forth. And see ground.
Now this is a more economical scope. Does it use the same, because this baby's got silicon germanium memory, it's got ultra fast converters, it's a beautiful piece of machinery.
Yeah, in fact, one of the best ways to make a scope lower price is to not invest so many millions of dollars in R&D development for a new chipset. So in fact, we use the same basic silicon germanium and the same core software in both of these lines of scopes.
So you got that great acquisition technology in both, in all your product lines.
We do. And where you might have a 10 gigasample ADC on each channel here that can interleave to 20 gigasamples, here we've got the same basic technology but at 5 gigasamples per channel, and it can interleave to 10 gigasamples. So we didn't have to spend multi-millions of dollars to design new amplifiers, new ADCs, new memory chips, new core software, and it sort of down deploys the technology and gives it to you for a very reasonable price.
Oh, that's great. That's great.
Let me show you one or two more things on the scope. So the first thing that you might want to do with this pulse is make some cursor measurements on it. Now,
right, we're always doing that.
Of course.
National.
And when we did a survey of scope users, we asked them what do they do with their everyday bench scope, and they said, okay, the first thing I do is I get the signal on the screen. I just want to look at it. So make that easy. So we did. They say the second thing we do is we turn on the cursors, and we want to measure something. Now, again, with every previous oscilloscope, including LaCroix scopes, you had to find the menu for cursors.
Right.
But here, we got knobs for cursors. You turn the knob, and look, the cursors come on.
Oh, that's beautiful.
So there's my cursors, and I can make a measurement,
Snap
and they're right
calls.
there. And I never had to find a menu.
That's great.
You turn the knob, the cursors come on.
Now there's a mouse here. That mouse operates a cursor as well as a touch screen.
That's right.
So you can do either. If
it's
you
a
wanted,
touch screen, and if I wanted to do something with the cursors, if I wanted to just turn the cursors off, I could do that. But it's also
plug a USB
it's
mouse
Windows
in the back.
Yeah, in fact there's even a USB port here on the front. That's one of the things people requested. You know, if you want to plug a USB device, you know, usually you have to like crane your head and look upside down and figure out which way to plug your USB device in, and it's hard. And they said, you know, why don't you just put a USB port on the front of the scope?
Right.
Yeah, it's such a good idea. It's like as soon as somebody said that, we went, well, why didn't we think of that?
Well, I have one of those little USB memory sticks.
Yes.
I'm always sticking it in my Dell computer to take a file home, to take a work file home and stuff. So that's great.
Yeah. So in fact, if you want to save your favorite front panel setup for making measurements, you can plug that in here on a memory stick. Or if you want to plug in a CDRW and record a lot of data, you're writing a paper or something like that, just plug it right in here. It's USB 2.0, so it's fast.
So you've got all the benefits of modern PC hardware, including this incredible deck of data acquisition that does the gigasample data acquisition.
That's right. That's absolutely right.
And it looks like you've been listening to your customers. How'd you come up with,
well,
you know, this product?
LaCroix was famous for making sort of the most advanced analysis in the oscilloscopes. And we decided that we wanted to make the world's best everyday bench scope. So we surveyed more than 200 scope users about what kind of scope they used every day on their bench. And we asked them what they wanted. They said, we want the best acquisition technology that we can get. So we're making precise measurements.
Yeah, that's LaCroix.
They want to have a good display. They want to be easy to use. You know, you don't want an everyday bench scope that's going to cause you frustration. Right. You want an everyday bench scope that's going to solve your frustrations, going to solve your signal problems. And in the best of all worlds, you know, if they lived in nirvana, they would like the scope to be a pleasure to drive. You know, it would just like be like getting their Ferrari Testarossa and driving home from work.
Right, something you don't dread having to use.
Exactly. So that's what we set out to create. So we looked at the kinds of things that people did with scopes, the things that were repetitive or were cumbersome or were difficult, and we tried to make them easy to use and even almost fun to use. Let me just show you a couple slides about the oscilloscopes. We talked about what people wanted in an everyday bench scope.
This is how the position of the model line, right?
Yeah. So here's the 5 models that we've got. They cover what I think is the broadest range of the most common kinds of scopes that people use every day on their bench, from 350 megahertz up to 2 gigahertz, with a good sampling rate on every channel, you know, ranging from 2.5 gigasamples per second up to as high as 10 gigasamples per second.
Wow, that's tremendous.
It is. It's nice. And they all come standard with a mega point of memory. Standard, no extra charge. So you've always got enough, you know, memory to capture those signals. If you need more memory, you can get it.
And that's that great silicon germanium memory.
It's actually, the memory is a very high-speed CMOS process, but the amplifier and ADC are silicon germanium.
Oh, that's where the silicon germanium.
That's right.
Okay.
And the prices are very reasonable. You know, immediately as soon as I show this slide, everybody says, yeah, but how does that compare to? So I made one slide here that just compares some of the 500 megahertz models that are out on the market here.
Various manufacturers.
And I can neither, you know, confirm or deny or recommend or not recommend any of these scopes, but I know they're out there. You can get these specs off the websites. You know, lots of people use these scopes, so they're a reasonable benchmark for comparison. And you can see the differences in sample rate and memory length and price. So the wave runners are, you know, like most things that are new technology. The newer technology tends to work better and be a little cheaper. So that's nice for the user. Here's something that sampling rate gives you. I mentioned that they have a good sampling rate per channel.
Gigasamples.
That's right. So if you wanted to measure a rise time and you wanted to say how accurately could you measure the rise time and then how repeatable the measurement would be, this is just a little experiment that I did on a scope. This happens to be a 1 gigahertz scope, but I could sample anywhere from 200 megasamples per second up to 10 gigasamples. But I'm using the same channel of the 1 gigahertz scope. So this column shows the ratio of the sample rate to the bandwidth. And this shows the measured rise time. Now, the real rise time was 1.15 nanoseconds. But you can see that I don't get the right answer when I have a slower sample rate. And the the measurement is not very repeatable either. You get a lot of variation in the measurement. And that's what this graph is showing.
It could cause all kinds of misinterpretations.
Exactly. So if you just made the measurement once, you might get the wrong answer. If you made it again, you might get the right answer.
So this would be why even your 350 megahertz bandwidth scope has gigasamples.
Exactly. It has a 2.5 gigasample ADC. So the ratio of the ADC sampling rate to the bandwidth is good.
That's critical for us because we publish this. It goes into a legal document, our data sheet.
Right,
so
right.
we've got to have, there's no question about the
If you want to
quality of our
characterize a
measurements.
part, you want to know for sure that the numbers you're putting down there are right, whether that's a published data sheet or something that you merely give to your boss and says, boss, here's the part that we've made.
Right.
So you want to have confidence in your measurements. You know, even if you just view the signal on the scope screen, having a higher sample rate will help you have a better view on the screen as well. Now in this particular picture, I'm showing a Tektronix scope, but it could be any brand of oscilloscope. But on the left-hand side, I've got the pulse sampled at 5 gigasamples using just one channel of the scope. And on the right-hand side, I've gone to using all 4 channels of the scope, and that means that the ADC samples at 1.25 gigasamples. And you can see that the view of the signal is not as stable when it doesn't have as many samples on the edge. And it starts to show this, it's called Gibbs ears actually, this artifact where you've got pre-shoot and overshoot that's not really in the signal. This is the real signal shape. So you can even get problems in the viewing of the signal if you don't have enough sample rate. So higher sample rate is a good thing.
Can't have too much.
Yeah. Now my last slide is on probing. Most people use a probe at least part of the time.
Yep.
And if they could, they'd like to get away with using a passive probe because they're cheap, they're physically robust, and they tend to be handy. Everybody's got some passive probes. So we've got a nice new passive probe, and it comes standard with the scope, and you get 1 probe per channel on the scope.
So you get 4 probes when you buy
get 4
this?
probes with
You're
a
kidding.
4-channel scope.
Oh, that's
no
great.
charge, they're included.
That's
and it's
great.
a 500 megahertz probe. And it has a lot of nice things, and if you want to see all 15 accessories that come with it standard, or all 30 accessories that are optional, you know, you can ask your local LaCroix sales guy to bring a probe kit by. But I showed this ground blade here today, because that's something that's new. We've put a little foil on top of the chip, and we tack down the ground, so we can simulate the ground plane on the chip.
Oh, that's great.
And then we're probing it with this blade-shaped ground lead instead of the usual wire-shaped ground lead.
Right, which causes all kinds of ringing, we have customers that misinterpret that.
Exactly.
They say, what kind of lead are you using on your scope probe? Because no one realizes how much error you can get from that inductive wire that
and you've got some
lead.
capacitance and some inductance, and the two of those can cause you trouble.
Right.
So you want to have, people often ask what capacitance that probe is, but they often don't ask, and what inductance is the ground lead? And they probably should. But this blade shape of ground has much less inductance in this geometry than your usual wire shape ground lead. So it's a nice probe.
That's a clever thing. So you build a little ground plane on top of the chip, and this is great for us because a lot of the boards we work on are just so heavily populated now, 12-layer boards. There's no place that you can have pads handy that you could, even if you can control the layout of the board, you can't put that pad in to be able to able to check.
Well, sometimes you're lucky and you've got test points and you can probe them with normal probing accessories. But sometimes you're not so lucky and you need something that's a little more innovative.
Well, I can tell you guys have spent a lot of time in the lab to learn tricks like this. That's a great feature.
Well, you know, we use these scopes ourselves in our design labs. So we know the kinds of things we need, but we also talk to, as I said, hundreds of users about what they want in their everyday bench scope when we made this scope. So I think we've done a lot of things that people are going to find
this is
really
great.
nice.
You got the technology, you got the ease of use, and it's a fun scope to use. I'll testify to that.
It is.
I love it.
I spent my first 10 minutes with this scope, and I went over to the engineering group, and I said, you know what, guys? This scope is an absolute pleasure to drive.
Yeah.
I really like it.
Okay, well, thank you so much. It's been a pleasure, and hope to hear more from LaCroix in the future.
Thank you very much. I was glad to be here today.
Thank you.
Hey, Paul, that was an excellent LaCroix demonstration. I appreciate that. Now, who is our next lab segment sponsor?
Well, that's going to be brought to you. Our lab segment this month is brought to you by the Reed Electronics Group. Reed Electronics Group is the electronic industry's largest global information provider. They're making information work for both buyers and sellers around the world. Their featured publications include EDN, that's my favorite. They got a lot of analog in EDN. Joshua writes for them. Then Electronic Business, Electronic Component News, Semiconductor International, and Electronic News. So let's go check out the lab. What kind of good stuff you have for us this month, Bob?
Well, we have some amazing, not obvious measurements to do.
Micro-ohms,
Nano-ohms.
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 Come
Yeah.
on, here's
All
some
right.
Let's
Nano-ohms.
wander over.
All right, let's check this out.
And I kick that aside. No problem. Now, over here on the right, we have a basic linear amplifier. Well, it's almost linear, isn't it?
That's
It
the
clips.
audio amp.
That's the
It's an
audio.
audio amplifier. It's an LM3876, and is it? Ooh,
Is it
it's
hot?
warm. No, it's warm.
Not
Feel it?
bad.
No, put
Not
your,
bad.
put
You
your
can-
finger over here.
You can keep your finger on it. If
Yeah.
you can count to, what, 10, you know
Yeah.
it's not 70
So
degrees
this
centigrade.
is putting out an
Oh, that's
ampere
great.
at
You've
plus
got
or
it.
minus a couple of volts.
You can see it, the ammeter is
Yeah,
wiggling
the ammeter
over
is
here.
working to provide a current that's plus and minus.
So that's why they're going alternately.
Alternately, they are working hard to
Plus or
provide
minus 12
1
volts.
ampere.
There we go.
Yeah, hit that one. Bring it down a notch. We are, hope you get that waveform, yeah. So we're putting out plus and minus 1 ampere. Through
So that's
this
the excitation
load.
voltage.
Yeah, that's the excitation voltage, exactly.
And that's a conventional now. This is an XY plot. You're just looking at what we're pumping in to that bridge. So now
And-
we're kicked into XY, thanks
Now,
to
when we
Mr.
put this
Groy.
into XY, we have a signal that's wobbling around a little bit, but it is well behaved. And
So in the,
if this was sloping left and right, we'd have a lousy balance of offset. If we were sloping this way, we'd have terrible errors. We can put this in. Ooh,
It jumps all the way, because it's so sensitive. It's measuring the temperature.
we're talking about
just
1
from
part
your-
per million
Wow.
resolution.
Wow.
So here we have the current coming in on 2 wires into this signal where we have a separate power supply at plus minus 12 volts to distinguish the difference between this voltage and this voltage. And
And this
It
chunk
cuts
of
it.
wire, can we, it comes back. This chunk of wire is what you're measuring. A tiny
yes,
little chunk of
a
copper
tiny
wire.
little bit of 1
And it's
milliohm
actually
wire
measuring that.
at the part per million level.
That's
and watch
awesome.
it cool off. As it cools off, it's got very small error. Small error.
so as the bridge balances, it would go straight.
As the bridge is balanced, it will go straight. I think we can pull that back in. Anyhow,
You just have
so
these shunts.
we have precision resistors inside here. This is a Rubbermaid box. I measured this thing at the million megohm level. It has no errors.
Polyethylene's pretty good.
Polyethylene's pretty good. I moved this around to have this give no effect because this swings out so I can put any purchased precision 0.1% 1 milliohm resistor. Why do people need a milliohm? The main point is, if you're trying to measure 80 amperes, 1 milliohm is lousy.
Lots of watts.
You need 0.1 milliohms to measure resistors. How do you measure a 0.1 milliohm resistor compared to this milliohm resistor? So we do milliohm and sub-milliohm resistor technology to help people measure 80 amperes. I don't approve of 80 amperes to run any circuit on, but if you have to, yeah, you can do that.
I did an ECL test rack once, did 2,000 amperes. So now, where's the 200 ohm resistors that were the balance?
Oh, the 200 ohms?
Is it a pod or is that two discrete
No,
resistors?
they're inside there. Wait a minute, I can lift this up.
Okay. No hazardous voltages in this one.
No,
folks, So we're
200 ohms resistors are here and here, here and here.
okay.
Okay, and here and here. So we do fool around with precision 200 ohm resistors to help us evaluate 1 milliohm resistor. Okay?
That's great stuff.
So this is the error voltage we're looking at. We can move that around to detect small errors at about 3 hertz, because if you're doing it at 300 hertz, you're measuring inductance. At 3 hertz, you're measuring resistance.
and that's
okay.
what we're trying to do
That's what we're
this
trying
month.
to evaluate. Are these 2 resistors good? Yes. Do we have more resistors? Yeah, I got some 5 milliohm resistors, but I haven't got them here right now.
We can write that up and
We'll discuss
have it on
that
the
later.
site.
Yeah.
Follow up. That's great.
So here's the first amplifier, second amplifier, third amplifier. Pretty good stuff.
High gain, low noise.
Yeah, low noise. Thank you.
Okay. Thanks
Next
a lot.
question.
Let's get back and
Yeah, let's wander back
Talk
and
about-
discuss any other technical questions.
So we got some new stuff. Paul, what have we been working on lately in the amplifier group?
Well, we just published our new amplifier selection guides with all the latest and greatest LMH parts. This is, we have both the high speed and the low voltage, low power selection guide. And these are also available at amplifiers.national.com. You can download them. They're PDFs. They're not that big. But here we're showing our new LMH 6559 and 6560 high-speed buffers, 1.7 gigahertz
Wow.
high-speed buffers.
What process?
Can I have a copy of that? Because I haven't seen this stuff, man.
Well, you've been on the road for 30 cities. Bob just got off the analog
I need a
seminar.
copy then.
There you go, right there.
Well,
Right on the
good.
front page.
Thank you. I want this. I'll read this when I get home tonight.
What process do we use for this LMH?
VIP10.
VIP10? That's a dielectrically isolated
Yep.
process, right? That's
our
why it's so
latest and
fast?
greatest.
Oh, that's great stuff. Okay, that was interesting. We had some questions from the last show, the watt meter show.
Okay.
One of the questions was, why did you use that old-fashioned analog stuff to make your watt meter? Why didn't you do it digitally?
Well, an analog watt meter can provide dozens and dozens of kilohertz of bandwidth. Anybody who wants to try that with digital stuff, go ahead and try it. But you can have A to D converter dynamic range problems, A to D converter bandwidth problems. It's
DSP.
kind of hard to do.
A lot of current to run the
Not
DSP
even
and do all that
No,
multiplication.
you don't want to screw around with that. Analog stuff does very good bandwidth and very good dynamic range. Like, as we noticed, 1,000 to 1, 10,000 to 1 dynamic range.
And your
So,
bandwidth, you got up to what, 30K, didn't you? 30 kilohertz?
You need to have a good sensor.
Low
layout,
inductance.
A low
Low
inductance
inductance.
sensor to get good bandwidth. So that's what you have to do to get good results.
Great.
Be happy to discuss that any old time. You know where to find me. rap@galaxy.nsc.com. And we'll be happy to explain why these analog circuits are working so well.
Okay.
You got another question?
There wasn't.
No?
We had
You
one,
had another
yeah.
question.
We had a couple more questions.
Okay,
One about
ask away.
the. Could you use a multiplier chip? Some big dollar multiplier chip
you can
to
use a multiplier
multiply
chip.
volts times amps to get your watts.
Yeah, but you'll still have to use a trim procedure with any good precision analog multiplier to get the right kind of dynamic range you're looking for. So
You might get the speed, but then you still got dynamic range problems.
I don't know if they have the speed. They may have good speed, but they will not have precision at all speeds.
Okay, we had one more question. Somebody wrote in wanting, they hadn't even seen this show where once again you use the LM394. They wanted to know why you use that 394. It's an old part, right? We've been making this part how long?
Oh, well over 25 years.
Wow.
Yeah. But it's a good old part. And people like it because it works so well.
And for the people who don't know what the LM394 is,
please.
it's just a simple transistor pair. It's a differential pair.
Matched
But it's,
though.
but it's
matched differential.
precision matched well below 300 microvolts offset, typically 10 or 20 microvolts offset. So when customers use this, because we recommend it, they love it because it does so well.
And you can see, you can trade off current noise, voltage noise.
True. You can get the voltage noise or current noise covered as a balance, and we have an app note on that, which is AN2222. So we'll be happy to recommend you to use the LM394. Even though it's kind of old, it works so well. Customers are very happy when they use this.
And we're happy when our customers.
Yeah, that's the whole main point.
Okay, thanks. That's all the questions we have.
Okay. Friends, thank you very much for coming to this webcast. And we've got Paul Rako here and Paul Grohe, and we enjoy talking with you guys. And if you have any questions, we'll be happy to discuss it with you. Thank you very much. Bye-bye. Bye.